In this video, we will be reviewing homework 2 for quality management. So let's begin. The first question is about Weston Electric Company. They have given us some data on light bulbs. If you click this Excel file and download it, I just did that. This is the data that you're given. Okay, and you have to find the upper control limit. The question tells us that this is for the Xbar control chart. It does not need to. It could just say find the upper control limit for the appropriate control chart or charts, and you may have to determine what control chart to use and then find the upper control limit. Now, which chart to use depends on the type of data. Okay, so we know that this is the lumens or the intensity of the light the bulb gives out that's given. This is a numerical value. It's not a 0-1 value. It's not a count. It's a numerical measure. So we are going to use the X bar and the R charts to control this process, the manufacturing the bulb process, make sure all bulbs give off sufficient light. So a few things to note here. What is our sample size? We have 5 samples. That is not the sample size. Sample size is how many values you have in each sample. So the rows give you each sample. So how many values are in a row? We have 1, 2, 3, 4 observations per row or per sample. So the sample size, which is called N, equals 4. Okay, this is very important. If you think N is 5, your answers would be incorrect. So N is 4. Okay. So for X bar R chart, for each sample, you have to find some sample statistics. So for sample 1, 2, 3, 4, 5, we need to find the mean value or X bar value, and we need to find the range R. So Excel makes it easy to do that with the formula. So we can use equals average formula on the values in that sample to get the mean value for each sample. That's X bar. And then the range is simply the maximum of these numbers minus the minimum of these numbers. Be careful when you enter this max minus min formula that you do not select the X bar value. The max and min are based on the actual observational data, not on the average value. So make sure you don't, by mistake, drag your selection to include this 601. Okay, so the range for the first sample is 24. We can just drag it down, get range for each of the samples. Okay. With these statistics in hand and knowing the sample size of 4, we can now calculate the control charts for this data set. So to do that, we'll go to our slides. We scroll down until we find the X bar R charts, which are after process capability, which are right here in this section on statistical process control. Okay. And here is the formula for the range chart. Okay. And here is the formula for the X bar chart. So we need the mean of the means, the grand mean, and we need the average range, and then we need this value called A2. A2 can be found from this column, this table on slide 41. So we actually need A2, D3, D4, all of these constants. We only need to know the sample size to look up these constants. Our sample size, remember, N is 4. So we go to this table and we find for N is 4, A3 is 0.73. So we can write our constants here. A3 is 0.73. Okay, and then we need D3 and D4 from the same chart. When N is 4, D3 is 0, D4 is 2.28. Okay, now we need X bar bar for this formula. X bar bar, that's the mean of the means. So it's going to be the mean of these values. So my X bar bar will be the average of the averages. So the average of these values. And then my R bar will be the average of the range values, because the bar represents an averaging function, and I have all these range values. If I average them, I get R bar. Okay. And so these are the key values. These two values plus these values, we can find everything. So for the X bar chart, we have upper control limit and lower control limit. And then similarly for the R chart, we have the upper and lower control limits. For the X bar chart, the formulas are simple. You take the mean of the means and you plus minus the A2 times the R bar. So we take the mean of the means right here. For upper control limit, we plus, this is A2, not A3, so I've mislabeled it. This is A2, okay, A2. That's what the constant is called. So we take X bar bar plus A2 times the average value of the range, okay? And then for lower control limit, we take X bar bar minus A2 times the average range, okay? So these are our control limits. And then for the R chart, the formulas are right here. It's D4 times R is the upper control limit. D3 times R is the lower control limit. So upper control limit is D4 times the average range. R bar means the average of the ranges. And then the lower control limit is going to be D3, which is 0. Anything multiplied by 0 will give us 0. So this is, these are the answers. The control limit for the X bar chart and the R chart. Now we go back to our question. The first question asks us the upper control limit for the X bar chart. That'll be this value. It wants it to 2 decimal places. So we can format in Excel to only show 2 decimal places. And that's going to be 614.55. Okay. Okay, question 2, lower control limit, that's going to be 581.85. Okay. R chart upper control limit is just going to be this number, 51.07, again 2 decimal places. And then question 4, lower control limit is just 0. Okay, so after these control charts have been established, we take a new sample with these values. So we are going to get, sample 6. So get a new sample, and this is, a new sample. So this sample was not used previously to make the control charts. We're now going to start plotting new samples on the control charts. So we get 625. 592, 612, and 635. And these are the values. And now I want to check, is this sample, in control or not? How does it compare to these control charts? To plot any sample or to compare any sample with the control chart limits, you have to find the sample statistics, which is in this case X bar and range. So we just drag the formula for the average down right here like this. Excel automatically did that because it sees I'm just extending the table by adding a row. So the average of these 4 values is 616. The range is 43. Okay, so here's what Excel has done. This was very tricky. I was wondering what happened. Because if you go up, we entered 614 here, and it changed the 614 to 620. So it almost tricked me. What happened is it changed these 2 values when I added this row. We have to make sure these values don't change, because the new sample is not going to be used to determine the control limits. That's already been done by the first 5 samples. The new sample is going to be plotted on the control charts. It's not going to affect the control limits. So I have to adjust this formula to not use, the X bar bar is not supposed to be affected by the new sample. So this is supposed to go up till here. And this is supposed to go up till the other one too. So this is my control limits, and these are my control limits. So for the new sample, right, I'm just going to move it out of this table to avoid affecting these values. Okay, it's probably just better to keep it outside the table. Okay, because I don't want this to affect the Xbar bar and R bar. I don't want to affect these values here. These should stay the same, what we put in up here. So the new sample 616 is outside the, is higher than the upper control limit of the Xbar chart. And 43 is okay, fine. So if you are out on even one of the two charts, you are out of control. Okay, so let's look at our options. Process is in control, nope, because you exceed the Xbar chart limit. Process not in control, this is true. You don't have to exceed both charts. If you're out on one chart, you're out. The sample exceeds the on the R chart, nope, R chart is fine. 43 falls right between 0 and 51. Xbar chart is the problem. 616 falls outside the upper control limit. So these are the two options that are correct. Okay. Notice these square boxes. You can have this is a multi-choice answer. Not a multiple choice. It's a multi-option answer where multiple answers can be correct. Okay. So it's not regular multiple choice where you only click one. That has those round boxes where if you click the other one, it moves down. You can't select more than one. So in this question, we can select more than one. More than one option may be correct. You have to get all the correct ones to get full points. Okay, so that was it. So make sure Excel does not, when you get the new sample, make sure the new sample is not used to update your control limits, because you calculate the control limits when the process is in control based on some testing data, and then when you run the process, then you don't update the control limits. You just plot the samples and compare them versus the control limits. So make sure that does not happen to you. Okay, I almost got the question wrong. Because when I added the row, Excel updated these two formulas. Okay, so that was the first Xbar and R chart question with multiple parts. Now let's go to the next question. We have a highway safety department monitors accidents at the intersection of two highways or roads. Accidents have averaged 3 per month. What type of control chart should be used? So we have to ask ourselves, is this 0-1 data? Which it is not, because it's not saying whether there's an accident or not an accident. It's not saying the probability of accident is this. It's saying how many accidents have happened per month. So it's not 0-1 data, so we can exclude the P chart. It's not the P chart. This is a traditional MCQ. You only select one option, right? So only one of these is correct. So it's not the P chart. We can exclude that. Now it's either going to be a count data, count of something occurring over a period of time, or a period in space, like a plot of land or a mile of highway. A unit of space or time either could be used for a P chart, because Poisson distribution can apply to count data across over time or over space. So that looks like that count of something happening over a month at a particular point. That sounds like C chart. And then Xbar or R chart, it doesn't look like that because you're not measuring something. You're not measuring the speed of cars. So, you sample 10 cars and find their speed. It's not like that. It's the count of certain something happening, which you want to control. You want to control accidents. You don't want to have too many accidents, and it's the count of that thing happening. It's not a measure of a physical quantity like speed or force or weight or volume or, intensity of light, things like that. So it's going to be the C chart. That's the right answer. Upper and lower control limit for the C chart. C charts are kind of easy to handle because you can calculate the C chart just based on the average occurrence. So we had 3 accidents per month. That was the C bar. and you just need the C bar because the standard deviation of C bar is simply square root of C bar. And so we can find this value by just doing square root of C bar. And then Z is going to be 3 by default if it doesn't specify a sigma level. It does say use Z equals 3. So if it says 3 sigma control chart or Z equals 3, we use Z equals 3. If it says 4 sigma control chart, we use Z equals 4. If it says 2 sigma control chart, we use Z equals 2. So for this question, we have C bar equals 3, then sigma C bar is going to be square root of that. Okay, and then upper control limit and lower control limit. We need the Z value, which is 3. It's a 3 sigma chart. So we take 3 plus the Z value times the standard deviation, which is square root of the mean value. And then we take the mean value minus Z value times the square root, the standard deviation, which is the square root of the mean value. This gives us negative. Now remember, counts usually cannot be negative. You can't have negative 2 accidents in a month. And so because negative numbers don't make sense in this case, this will become 0. So upper control limit to 2 decimal places will be 8.20 because the 9, the 6 will round up to the 9 to a 10, which will make the 1 become a 2. So you'll see it'll become 8.20. Okay, that's the upper control limit. And then the lower control limit is going to be 0, although it is minus 2.20. You can't have negative accidents, so we just make it 0. Okay, so we are making good progress. Let's get to this Arizona Bank question. Okay, and this has an Excel file, so let's download that. And let's look at our data. So what are we doing? We are verifying accuracy by checking random sample of 250 records. Okay, a record containing 1 or more errors is considered defective. So whether you have 1 mistake or 10 mistakes or 5 mistakes, that's defective. So it's yes or no, defective or not defective. Results of the last 30 samples are given in the Excel file. So sample 1, out of 250 documents that we examined, 7 were defective. Sample 2, out of 250 documents we examined, 5 were defective. So what type of chart we'll use is Xbar. Our chart is out of the question because it is like 1-0 data or count data. And so the question is a P chart or a C chart. Okay, it's not a count of defects happening over a period of time or space. It is we take a sample and we classify everything in the sample as yes, no, 1-0, defective, not defective. And so the actual data you have is something like this. So sample 1, and then you have document 1, document 2, document 3, document 4, document 5, all the way down to document 250. Okay, like that. Okay. And for each document, you say 0, there's no defect, it's fine, 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 fine. Or maybe document 6 had a defect, so that's a 1. 0, 1, 0, 0, 0, like that. So that's your raw data, okay? But what the question has done is it said in all of the first row where you have 250 documents that you examined, 7 of them were 1, which means they were defective. So I'm just going to, instead of writing like, 243 zeros and 7 ones, I'm just going to write 7. So you know that out of 250 documents examined, 7 were defective, 243 were fine. So it's like a summary way to express this 0-1 data, but the underlying data is 0-1. So it's not going to be a count, it's going to be a P chart. Another hint that it's a P chart is you have a sample size. In P charts, you do have a sample size. You take a sample and each member of the sample is classified 0 or 1. In count data or a C chart, your sample could be just one thing, like one car. How many defects are there in one car on average? Okay, each car we make has like 2 defects or whatever. That's your C bar. So it's not like a sample of cars and each car is 0-1, right? Or you have, okay, over this time period, how many of this event occurred? How many rainfall we had, how many days of rain we had over a month? okay, things like that, or how many scratches we have in 1 meter of cloth. Maybe we make cloth or textiles, right? So the unit in terms of space is 1 meter, and we just count the number of defects. It's not that we're examining different pieces of cloth and saying this cloth is fine, this is bad. We're not doing 1 0 and discarding things, just counting defects over a piece of cloth. So that'll be a C chart. This is samples, and for each member of the sample we say 1 or 0. So this is going to be a P chart. Okay. Now, very important to remember, sample size n is going to be 250 because each sample has 250 members, right? We have 30 samples, but that's not the sample size. Number of samples is not the sample size. Sample size is how many members or objects do you have within each sample, which is 250. So n will be 250. We have the upper and lower control limits. We have to use the 3 sigma control chart, so Z is 3. So if you go to the slides, the first thing we have to find is P bar. Okay, P bar is total number of defectives divided by number of samples times sample size. So the total number of defectives, we can do here, let me delete this thing I made to explain to you guys how the raw data would look like. Okay, so let's do it here. So total number of defectives, that's going to be a sum of this column across all 30 samples. How many defectives did we find? Okay, and then P bar, which is the proportion of defective, is this number divided by number of samples, which is 30, times the sample size, which is 250, and we get P bar of 0.04. Okay, now once you have P bar, you have to find sigma P bar, which is this kind of complicated looking formula. But once you have sigma P bar, the UCL LCL calculation is really simple. You take P bar plus Z times the standard deviation of P bar, and you take P bar minus Z times the standard deviation of P bar. So let's find sigma P bar. Okay, so sigma of P bar is going to be a square root. So this is how you find a square root, equals square root, and in brackets you type whatever you want to take a square root of. That's the square root right here, the outer square root. And then within the square root, in the numerator, you have P bar times 1 minus P bar, and then you divide that by n, and you take a square root of the whole final thing. So we're going to take P bar times 1 minus P bar, and then we'll divide by the sample size n, and that's going to be our sigma P bar. And then Z is 3, so UCL, LCL now become easy. Upper control limit is going to be P bar plus the Z times the standard deviation of P bar. Okay, and then the lower control limit is going to be P bar minus Z times the standard deviation of P bar, which is this, so 0.0772 and 0.003. 28 is like 3. So let's see how many decimal places we need to keep. We need to keep 3 decimal places. Okay, so we can just round them both to 3 decimal places. So 0.077 is the upper control limit. And then the lower control limit is 0.003. Okay, so that is great because in this homework you've already seen all 3 types of control chart that we have covered. You've seen an Xbar, R chart, which is the first question, what's an electric company. Then you saw a C chart, a count chart, and then you saw a P chart. Okay, so let's see what's left. So now we have some chicken we're working with, and we are trying to control the portion sizes in our manufacturing facility, and we have to find the process capability ratio and the process capability index. Okay, so we can just go to our slides, go all the way up under process capability. We have the formula for process capability index, CPK, and we have the formula for process capability ratio, CP. So upper spec minus lower spec over 6 times standard deviation, and then this one uses the center of the process, which is Xbar bar as well. Okay, so let us make a new sheet, and here we'll do the process capability questions. So for the question 1, when you need the process capability ratio, you're going to need upper spec. This is not UCL. This is not UCL. Do not confuse upper spec with a control limit. Specifications come from the customer, their voice of the customer. Control limits come from process data, their voice of the process. Do not mix voice of the customer with voice of the process. Specs are different than control limits. Conceptually different, qualitatively different. They're just a different animal. Specs are just coming from your engineering design or the user. Engineers take user preferences and then they write them down as detailed specifications of a product. And so those detailed specifications are there to satisfy the end customer. They have nothing to do with the voice of the process, what's the variables in the process. They're just the specs that will satisfy the customer. Those are upper and lower spec for process capability. Okay, so what specs do we have? Pioneer states on the packaging that chicken servings must contain 400 plus minus 100 calories each. So these will be our specs, because when companies put things on the label that their product meets certain standards or certain guidelines, then that is the spec for the product, because you have to meet that spec. So the upper spec is going to be 400 plus 100, because you could be 100 above 400, so the highest you could be is 500. And the lower spec will be 400 minus 100, because the lowest in calories you can be on a chicken is 300, so piece of chicken. So that you are packaging and selling. So your piece of chicken has to have calories within this range, 300 and 500. Now we need to find, if you look at this formula for CP, so we got the upper spec and we got the lower spec. Now we need to find the sigma, which is the standard deviation of the process output. This is voice of the process. What is the process saying its standard deviation is? Pioneer finds that its current process produces chickens with average of 420 calories and standard deviation of 25 calories. So for process capability ratio, CP, we don't care about the average, that's Xbar or the center of the process, where the process tends to be centered around. We only care about the standard deviation, sigma. So we're going to say sigma, this is of the process, is 25. We can find CP. CP is easy peasy, upper spec minus lower spec, divided by 6 times the standard deviation. Okay, a mistake students do is ignore this bracket, and then what this will do is divide the upper spec minus lower spec by 6, and then it'll multiply the answer by B5. You don't want to multiply by 5, you want to divide by B5 as well. So the whole denominator has to be in brackets like this. Okay, and that's 1.33, and we need to 2 decimal places, that's 1.33. Okay, now we have to find CPK, the process capability index. So now we need the Xbar of the process, okay, which is the center of the process, 420. This is the average value for the process output, long run average, center of process. It's called all these different terms. Okay, well, basically, on average, what does the process produce? So on average, this process produces chickens, breasts or pieces which are packed to be sold, which have 420 calories on average, right? So that's what it produces on average. So for CPK, if you look at the formula, we need the long run average of the process, Xbar, then we do minus the lower spec over 3 sigma, that's one computation. Then a totally separate computation, the comma means it's a separate computation, is upper spec minus Xbar over 3 sigma. And then of the 2 computations, we take the lower value. Okay, so I call them CPK1 and CPK2. So we have to calculate both of them and then take the lower value. So CPK1, we can take the average value. Oops, I'm on the wrong sheet. I'm working right here. So CPK1, I'm going to take the average value, and you're going to subtract the lower spec. This is very important. Don't subtract the higher spec from the average value. Look at the formula. Xbar minus the lower spec. The order of the minus is important because the negative sign can throw you off otherwise. So Xbar minus the lower spec. So we do that. Xbar 420 minus the lower spec divided by 3 times the sigma. Again, notice I put brackets around 3 times sigma. Don't forget these brackets, otherwise you'll just divide by 3 and multiply by sigma. You need to divide by both 3 and sigma. Okay, so that's your CPK1. And then CPK2 is going to be the upper spec. Now the order is reversed. You're taking the spec first, then the average. Okay, and then divide by 3 times sigma. Okay, and formulas are here, just formula, this formula. Upper spec was 500 minus the average 420, that gives you 80, divided by 3 times sigma, you get 1.0666. And now the true CPK is the minimum, okay, is the minimum of these two values. You can just see which one is the minimum. You have to put in this formula, you can just see this is the one, right? So that's our answer for CPK of 1.0666. Let's see how many decimal places we need. 2 decimal places will be 1.07. 1.07. Okay. So now this is interesting. Our CP was 1.33, which is fine. Okay, because it says compare the production manager wants to have a process capability of 1.33. Okay, they want CP to be 1.33. So on CP we are fine. We do meet that standard, but on CPK we are not fine because this one is below 1.33. So what does that mean? Okay. That means, let me see if I can find a place to draw. Illustrations. Yeah. Open board. Let's run this one. Okay, so this is what's going on. So, okay, you have 300 lower spec, 500 upper spec. Okay, the center of the two specs is 400. But your process is not at 400. Your process is centered to the right here at 420. And your process is centered at 420. Okay. So obviously there's variability in the process. Okay. So because this variability in the process is producing a lot of out of spec parts right here. Okay, it's producing a lot of these parts, out of spec parts, that have more calories than 500. Okay, how do we know it's producing out of spec parts? Because CPK is less than 1.33. 1.33, you still have some errors, but very few errors. But if CPK is not at our standard, then it's producing too many out of spec parts. Okay, so that's what CPK is telling you. Your process is producing too many out of spec parts. But is it producing too many out of spec parts because it has too much variability? It's too wide here, or because it's off center? Well, let's look at CP, because CP only cares about the width of the process. Okay, how wide or fat the process is, how much variability there is in the process. So CP is saying variability of the process is fine because CP is equal to our target value of 1.33. It's not below the target. So if you were to center the process, CP is saying that you will not be producing those out of spec parts. You will be like this. Okay. And your process would vary, but vary within the limits, and these out of spec parts would not happen if you just center the process. Okay. If CP was less than 1.33, then even with centering, you would not be fine, because then CP is saying your process is too wide. It has too much variability, even if you, because CP assumes process is centered. So CP is saying even if your process was perfectly centered, the variability would be too much because I am below 1.33, the comparison standard, right? Now, why do we compare to 1.33? That's like the 4 sigma level. That is up to the management to decide. Do you want 4 sigma quality, 6 sigma quality, 9 sigma quality? The higher sigma quality you want, the fewer errors you're willing to live with, the more accurate your processes have to be. So the manager said he wants 4 sigma quality, which is, value of 1.33 for both CP and CPK. And so, which is like 99% defect free type of standard. 4 sigma is like 99 point something, 99.9 or 99 whatever, right? Something like that, I believe. You can Google and find online exactly how much parts per million defects will be in a 4 sigma quality level. I think the slides might also mention that. Right here you have, if CPCPK is 4 and you're exactly centered, you have 32 defects per million. So 99 point something percent accuracy, very few defects per million. If you have a 6 sigma quality CPCPK of 2, then you'll have close to 0 defects per million. It'll be like 0.00 something, like, but it'll be approximately 0 defects per million. But if your process is not centered, then you'll get some defects per million. Okay. And here, if you are at 1.33 and your process is off center, you'll get a lot of defects per million, right? So 4 sigma, is very susceptible to drift. If you're not centered, you produce a lot of defects. 6 sigma is, very stable. Even if you are off center, you're still going to be very good, very low defect rate, right? So because CP is 1.33, we know that the variability of the process is fine. So the only other thing, if variability is fine, the only other thing that can be wrong is the process would be off center. And we see it is off center because the mean of the process, Xbar is not in the middle of the upper and lower specs. If it was in the middle, it will be a centered process. So we are having all these problems because we are off center, but our variability is acceptable. If CP was less than 1.33, then we'd have both problems. Then we'll say we are off center, yeah, because 420 is not 400. The mean of the process is not the middle of the specs. And if CP was less than 1.33, we'll also say there's too much variability in the process. Both things are wrong. Right now, only one thing is wrong because CP is 1.33. CP is fine. Only CPK is wrong. When CP is fine and CPK is wrong, then variability is okay, but the process is not centered. That's what throwing the CPK off. Based on process capability ratio, CP, process capable at the 1.33 level, yes, CP was 1.33. Based on CPK, process is capable at 1.33, nope, CPK was below 1.33, this is wrong. Based on CPK values, we can say the process variation is too much. We cannot say that because CP is a test of process variation. CP is saying process variation is acceptable. Based on CPK values, we can say the process is not centered. Yes, we can say that because variability is fine, but CPK is not fine. So we have to be off center to be messing up the CPK. Based on CP and CPK values, we can say that the process variation is low enough that process capability 1.3 can be achieved if the process is properly centered. Yes, that's exactly what I showed you. If you do center the process, CP is saying variability is acceptable. We will be fine if you are able to center the process. Otherwise, CP would not have been fine if that was not possible. So these are the correct options, and then you can submit your work. So that is it for homework 2. If you still have any questions, feel free to reach out to me.